Okay, let's try to get that unit test we were writing done. I did all my push-ups for today. So it is almost midnight. It's 11:18 p.m. I did my push-ups. I did 120. The goal was to get, just to 100 for the day. Ideally, I'm gonna try to do like 10 extra every week. So this week I'm gonna try to do 110 push-ups every day, right? And then eventually 120, etc., etc. And the idea is that at some point, my body should hit like a level of homeostasis where I'm getting enough exercise to where all of this extra weight from it's not just lockdown, it's also the drugs I'm taking, but all the extra weight should eventually go away. But well, that's at least my hypothesis. We'll see. I mean, there's plenty of like world record holder, super strong people who are also actually really fat. So I mean, that this might be in vain, but we're gonna try. So okay, so for this unit test stuff, we need to make sure we need to run it, and then this meg thing is going to be for the mega test index. I don't know if that's actually what I called it. What did I call it? Did I give it a name, or did I just call it meg and just let you guess as to what that means? It was a pretty nonsensical name. It wasn't exactly, it was not exactly something that had a exact definition. Now here, yeah, mega test index. That's exactly what it meant. And you need comments for that kind of stuff because obviously there's no way I'm ever gonna guess what that abbreviation stands for unless I make note of it somewhere. And it's one of those short enough abbreviations where I'm not going to put it into my shortcuts. Now I say that, but I have a really bad habit of making shortcuts. But usually, if it's 3 letters, it's too vague. Where it's there's not enough entropy in the there's not enough entropy in 3 characters to make me confident that I can give it a very specific meaning. So a 3-letter variable name could mean many different things depending on the locality of where that variable appears. So once again, it looks to me like something is taking very long. Okay. So is this thing that was taking a while? Okay, so now that we have this and it's failing on that other test that I think we're going to scrap, let's go through here and make some conditionals for changing how this is generated, right? So we're going to say that, if 0 equals meg, right? So if 0 equals meg, then B16, this is how we're going to generate it, right? And if 1 equals meg, then B16 equals, we're going to look at this table here. We're just going to call it big, or big end, big endian table, or I think we have enough room where we could do table big end. Well, actually, our function is, I'm just going to call it, I'm just going to call it big. And the reason I'm just going to call it big rather than call it big endian is because my local macros for this section are already 3 letters, so I just want to keep everything kind of normalized. So big, and then what we're going to do is, hold on, let me get some tea here. We want to use ink as an accessor. However, we can't go over, the number of test cases in here is 3 times 13, which is some number, 39, yeah, 39. So what we're going to do is going to do modulus 40 on this. So modulus 40 as the accessor. And that's how we're going to get it, right? That's how we're going to get it. Now, if 2 equals meg, then B16 equals, and this is where it would really help to have some type of JavaScript thing where we could have an inline function we could reuse, because I really don't want an external helper function for this unit test, because I would like the unit test to be self-contained. Now, we could use an include, right? We could write this code, block, and we know this code block is going to have to be exactly the same right here. So we could use an include to guarantee that the code is exactly the same. The problem with that is it just makes the code harder to look over and follow, because, oh, if I want to follow the logic of this code, I can't just glance from here to here anymore. I have to, like, open up the include file and take a look at that. It also makes refactorability harder. So even though what we're about to do is going to be very ugly, it is the simplest thing, right? So remember, I care mostly about rigidity, lack of abstraction, and ease to follow. So the things that people usually care about with code, like flexibility, ease of refactoring, those things, and like abstracting, like all of those things that people usually care about in code, I'm like completely the opposite. I don't care about those things. In fact, I wanna actively go against those things. So I have different goals in mind. So yeah, we have big, and then this isn't let, this is lit, right? Big and lit. Big endian, little endian, right? And then over here, we have, somewhere in this test section, yeah, we have our defines. So we're also going to define big, and big is going to be this huge thing right here, right? And then it looks like even if we wanted to call it big end, we didn't even have enough room. So then we're going to take this guy right over here, put it over there, right? So big endian array, little endian array, and these are 16-bit values. And then we're going to go make sure we undefine them, right? So after this section is done, we go on to undefine the big endian and the little endian, right? Okay, so we've undefined the big endian and the little endian. So it seems to be one viewer in the room. I don't know if that's actually just me or if that's someone else. But whenever I see one viewer, even if it's just me, I'll take the placebo. So maybe it's me, maybe it's someone else. But here's my demos. I'm working on a fractal auto tiling engine. That is my sales pitch. Okay, so anyways, let's keep on going here though. So yeah, we got the big endian, little endian thing going here. And those are just arrays of test data. So what we've done is we've just kind of added a little bit more complexity to this test, right? So this test right here, this test section is a cut and paste of this with some modifications. And now what we're doing is we're going to go through, so depending on what test value it is, we're going to generate these values in a different way, right? So we want this code to be exactly the same in both blocks, right? So generate gen, how about we call this at paired code, generate B16. 2021. So there we go. So yeah, we can call this at paired code generate B16 year 2021, right? So when I say at paired code, that just means that I have this code in two places and it needs to be exactly the same, right? So at paired code, we might also want to make absolutely sure that we know exactly what that piece of paired code is, right? So this is kind of hackish. It's kind of hackish and ugly, but it works, right? It works. It's very clear as to what it is. It's just kind of hackish and ugly, right? And I don't care about hackish and ugly. I care about working code. I care about code that I can understand. But if it's ugly, that's okay. Now, obviously, I meticulously align things. And that, when I align things, it's so that I can easily find mistakes in the code because I've meticulously aligned things. So it's not that it's not just, I don't just align things because it's aesthetically pleasing. I mean, I do that too, but the priority is just to be able to recognize patterns in the code by aligning everything. I don't even know why I'm in here. Why am I in here? Oh, yeah, so we want to go into documentation and open up our hashtag file here. And we just want to make a note of this, right? So, the paired code, right? At paired code. And we could, I don't know what we could do here. I guess we could take the actual paired code and we could dump it in here, right? To make a note of, here's what it originally was when we wrote this, right? So we could take this, and we could say, we could take a video ID. I know I just started the stream, but I might need to take a bathroom break here. Vid IID, and the video ID is 109, and the time is 42, because we want to be cool, and say, we use this exact block of code in both of our loops in the test code to make sure that the generated values are generated exactly the same way in the put loop part of the test as they are in the get loop part of the test. The goal is to put everything and then get everything. Doing so in a batched instead of interlaced order can help us detect memory stomping. Detect unintentional memory stomping. It's unintentional memory stomping we're worried about. Okay, so we have that. So now the goal is to just run this code again, and in our comparison, the mask. Ooh, the mask. Where are we getting the mask? The mask is right here. Okay, yeah. So we have. So it already works for generated values for different step sizes. So I'm just hoping that we run this and it does not crash this test, right? So I don't want to see mega test fail, and I don't want to see ducks deserve to die 2021. If I don't see that, and we get to this end message right here at the bottom, then we can remove this. We can remove this because the interlacing kind of test has the batch processing kind of test that we wanted to write. That is already been written because we just finished it. So if this passes, we're good for this, and we can remove this to do, and we're good. But I do need to take a break before we do that. So I know I just started, but let's do break. The timer. Okay, I'll be right back. Alright. The time has almost come to do more tests. Alright, time's up. Let me make a note here. Okay, let's turn the sound back on. Rearrange some windows here, and then we'll get to it. So, bottom monitor. Okay, so this thing, we're thinking once we get this running, we're thinking it's going to actually work. We're thinking this test code is going to pass. We're going to be done with this. But we'll see. This test code will pass, and then the other test code that's failing us, we're gonna gut it, I think. Either gut it or... yeah, I think we could just gut it, really. Sometimes... here's the beginning of this test. This is actually a pretty beefy test, isn't it? It is going through like a lot of data points, so it does make sense that it would be kind of beefy. But, oh boy. Yes, I mean, we got through that. Here's our little face here and here. We got through that, and then we fail on this thing here. So, I think... well, first of all, let's get rid of this. We're done with that. I think that this other test that we're writing is failing because we didn't know what the heck we were doing when we wrote it. And in order to salvage the test, it might make a lot of sense to just delete the test and start over, and kind of use this as like a template, right? Like I think that all this stuff here, I think we could steal all this stuff from here. We could steal all this stuff right from here, from this section. We could open up like a little notes file over here. We could steal all this code, and we could reuse it. We could reuse it for the test that's failing right now. So the test that's failing, let's go look at that for a second. So we go look at it. We're gonna find like a whole bunch of hard-coded nonsense and a whole bunch of like weirdness, and we're gonna say this stuff that we're like blah blah blah, do something. I don't know what's going on. Let's delete that. Okay. Now for this code, I believe it got way out of hand. We might have put like an include in it. It just got way out of hand. So let's look at this and be like, well, what can we do with this? Well, first of all, one of the problems with this test was like we got this get function here. And we're trying to like put and get, right? So, but instead of using the putter, we kind of like manually put the data and then tried to get it. And I think some of our logic for how we do that, like here's our PAINT5. Yeah, we use PAINT5D put, right? Instead of yeah, we use PAINT5D put here, but this corner txt y thing, does it give us a corner in terms of this canvas? Or does it give us a corner in, it gives a different corner based on the exponent. So it kind of makes sense. The test kind of makes sense. I'm really thinking we just should nuke this test. I don't know what that's about. I'm gonna nuke that. Yeah, so right here, what are we doing? So layer, tile quadrant, offset dex, right? And we're trying to get a value, right? We get a value. The problem here, I think, is that there's memory stomping going on, so, layer, whatever. Oh, I see. So we're trying to set a different exponent value. Trying to set a different exponent value. Offset dex. Tile exponent. Now the tile exponent, this put value, the value that we're putting here. Oh, we're getting covey picks. And then are we putting a value? Where are we putting a value, right? We're getting a value. Okay, so this is already after we've done that. This is the other loop we're putting in. So this value here, this put tile value, needs to somehow be composed of all the different, all of the different tile sizes possible, right? So we're going through the tile exponents, right? The put tile. The put tile value here. UTC in. So what is UTC in though? What's unit test in? What is it? Is it this thing here? Well, these are bit values. So I kind of see what we're trying to do here. And and we had it partially working before. So UTC in. Now that put tile value should be like we're extracting something from it. So right now we're never hitting bad generated expected values. So I don't know if we want all this cruft in here to... Okay, so everything here is like... The test really only begins right here. It's the simple get put test. We're going to loop through everything. We're going to go loop through the layer and the tile size exponent. And the tile size exponent, we're going to, based on the tile x size exponent, we're going to take the put tile value that's extracted from here, and we're going to put something for each offset dex. No, the offset dex should have a hand in calculating the value to put, though, here. So we have offset dex, and this tile value, the put tile value here, this is tab UCT in dexodat. Oh no, the tile value is already a 2-bit tile value, so that's fine. And then we're kind of packing, as we go through here, we pack in based on the tile size exponent. Okay, that makes sense. So we're going to go through every tile quadrant and offset dex. What, not layer? What about layer? Where's layer? Okay, so we are going through every single tile size exponent. Now, why are we going through every single tile size exponent? Well, then that makes sense. So every single tile size exponent and everything, and we're going to put a different tile value. And the tile value needs to depend on the tile size exponent. And it looks like when we look up the value essentially is kind of created from looking that up. And then we're going to loop through, again, layer, tile size, exponent, tile, quad, offset dex. We're going to loop through it all again. And make sure that everything looks the same, right? So we're going to get the corner, we're going to look for TX and TY, we're going to get the corner locations. And we're going to take PAINT5D, convert it to CovPix. And then we're going to get CovPix using the layer and the offset dex. And then we're going to see if those are correct. And they're not correct. Okay, so I do see what's going on. But the thing is that we're not directly using the getters and setters. And the thing I see that might be wrong, this TX, TY is in terms of PAINT5D, right? This is, we want to get the corner PAINT5D location depending on oh, I see. I see. My corner location is off. That would make perfect sense for why the math doesn't work. So let's look at a diagram here. So we're trying to get the corner in terms of PAINT5D, not in terms of this diagram. Hold on. So we're looking at this diagram, we're thinking, oh, we want this corner, this corner, this corner, and this corner, right? Well, we haven't really made up our mind to get those different corners, right? To get those different corners to where there's no overlap, this quadrant has to, the quadrant and the TX, TY, they have to be paired together, right? Because this is going to be a TX, TY, where TX, TY is 0, 0, and the quadrant is 0. This is going to be a TX, TY, where we're over here. So the TX-TY is local. It should be a local TX-TY, right? So since it's a local TX-TY, it's local to like one of these kind of blocks. Okay, so I see where the mapping is going wrong here. So more breakpoints. I see where the mapping is going wrong. And I see that we kind of want our loop to be connected with the layer. If we want to do something on this quadrant for one of the tests, this quadrant for another one of the tests, this quadrant for one of the tests, etc., we want to do different corners for each one of these tests. Well, this quadrant this quadrant is going to change what those corners end up being. And so I see what's going on here. So let's look at this get corner code and see, well, first of all, get corner, that's pretty vague. So PAINT5D tile exponent to max coordinate. So this coordinate sure looks like it is in terms of the PAINT5D space. So we can see this, and we can see this is kind of wrapping things. But yeah, tile exponent to maximum coordinate. So this code, here gets this code so we can make a note of that. Of 42 because we want to be cool. This code gets the maximum valid coordinate depending on the till x. The coordinate is in terms of a diagram. Right, we can take the diagram. So it's not this diagram we're getting the max coordinate. We're getting the max coordinate for a local thing in here. And so the diagram is, this is the diagram, and the file is paint5d.data. Okay, so now the thing is that this statement here is true in both of the functions, right? So for the x and for the y, so this is tx, so let's go over to ty here and just say, hey, ditto. And we can just say, instead of 42, we can say, oh, this is 43 now. 43, and this is the same exact code except for ty, right? So it gets the maximum valid coordinate depending on the tile exponent. The coordinate is in terms of, okay, so it doesn't always get the maximum valid coordinate, right? It gets it's the maximum valid coordinate, or it gets the corner, right? Together it gets the maximum corner value, right? So it doesn't actually get the maximum coordinate. Gets extreme, gets 1 of 4 extreme corners. Yeah, it gets 1 of 4 extreme corners, and it gets 1 of 4 extreme corners local in local partition. Local partition size based on till x, right? So that's what we're actually doing. Okay, so we're going to take this. We're going to change the time here as we screwed it up, or do we not want to change the time here? Actually, let's not change the time here. Say, we'll just say at 109, we actually are done explaining, right? So 44, and how about 42, because we want to be cool. No, it's going to be too long. Let's say 36, but by the time we make up our mind, it's going to get to 42. So we'll just say 42 to be cool. But yeah, at this time, done explaining. And then we can copy this. And it's the same deal. We were kind of wrong here, so let's override that. And this can be set to 55 for done explaining. But yeah, we're done explaining what's going on here. But now that we see this, we're like, ooh, okay, I kind of see where we're going wrong. So this test is still pretty good. It's just that when we go through these test indices, we want to, depending on that corner value, want to set everything in the upper corner here. We want to set everything in the upper corner here for our test, or the upper corner over here in our test. Or like down here, we want to set things in the corner over here. Or over here, we want to set things over in the corner in here. Like, that's kind of how we really want to do it. If we don't want to kind of like memory stomping. That's the way we're going to have to do it. And so we can keep the layer thing, but this tile quadrant needs to change for this to work properly. Depending on the corner value, you actually want a different tile quadrant depending on the corner value, rather than kind of hard coding it like this. If we want to avoid stomps, now, or can we actually go over here, set something over here, set something over here, set something over here, set something, and if we only set one thing, then we'll also be okay. The memory stomping, well, let's think about that. It seems like we should be able to do this fine. Except this thing right here. We go through the layer, the tile quadrant. Oh, hold on. So this corner here. So this still looks like it'd be good. It still looks like it'd be okay. But, because we take this TX, we take this TY. We convert it to covey pics, right? Now the problem is, I think the problem is the translation from these coordinates into covey pics, right, for the first loop, and the second loop over here with this put, there's an implied conversion from these paint pics locations to a covey pics location, right? So, is there a possibility that these calculations are just wrong, right? We didn't really test these, right? So, so I kind of see hope for this test code kind of working, but for it to work how I think it should work, we're going to need to make sure that our coordinate conversion kind of works. So layer, tile exponent, tile quad, offset dex. That actually makes sense. The layers aren't going to overlap. The tile exponents, they do overlap, but when you do it enough times... Is this the getter, though? Hold on. Loop through again. Check your outputs. So the tile exponent here, how does that affect things? Oh, I see. Okay, got ya. So, we should be able to, for many different tile exponents, for all the different tile exponents, they should all evaluate to the same. So here, so let's make a little test for this. So here, let's take this, and this is a test code we wanted to paste, because we thought it would be good use. So, but let's try to fix the test we've written. So, what I'm thinking is... how do we write this? We didn't write it like that, but now now it's this way. Sure, why not? Why not write it that way, right? So for a, for the corner depends on the tile exponent value, right? So tile exponent gets a different tile y. Depending on the tile exponent, we get a different tile x. And then we get this thing here. Oh, that I already pasted that. Never mind. Then we get this thing here, right? Want to convert this tx ty here, and PAINT5D to CoveyPix, right? And then later on we do the loop again, don't we? No, we don't do the loop again. CoveyPix, right? So somewhere we do CoveyPix to PAINT5D, right? Oh, we do a PAINT5D put. Right? So we do a PAINT5D put. So for a certain local tx, local ty, which is in an extreme corner, we're assuming that the output won't change. So we're thinking that for, you know, t for the tile exponent equals 0, and then tile exponent is less than or equal to 0, or less than or equal to 8 minus 1, and then tile exponent plus plus, right? So for this loop, we're going to use the same tx ty, so we can keep this out here like this. We're going to loop through here to get CoveyPix, and we're going to expect the same value as the first time it was used, right? But does that make sense? Oh no, because for different tile exponents, the local coordinate is different, right? Like, the local coordinate for the largest tile, tx, ty, well, that's just 0, 0, right? We lose information, and we can never get back to that extreme corner. Okay. So when we're using this, if we want any of this craziness to work the way we think it should, then the exponent size would always have to be the smallest exponent size, right? If we can use the smallest exponent size when we set something, then this code will work. But otherwise, it's going to fail. The reason it works for the upper left corner is because for the upper left corner, we don't lose any information for the coordinates, right? 0, 0, no matter what tile exponent we're on, we always get 0, 0, and that's what the reason it works. Okay, that makes sense. So okay, yeah, so I see what's wrong with this test. So the tile exponent size is really what's going to screw us up here and make this not work. And what I think I'm going to do is say, okay, so I see why it's not working. Because the way we kind of set up this coordinate conversion, yeah, that's not going to work. We're going to lose information, right? So here's the thing. We're going to write a test like this so that we can understand why this test really can't be jerry-rigged to take different corners, right? So So we're gonna get rid of this commentary eventually. But yeah, this corner to target thing. Yeah, we're just gonna get rid of this. Corner to target. Bad idea. We kind of jerry-rigged it because we thought, hey, we could be more thorough with our test and catch edge cases, but all we did is ended up writing a really bad test. So what we're gonna do here to get this just working, to throw this together, to get it working, is we're just going to say int32 corner to target equals 1. And we're going to make a note here. We're going to remove this and say, just make a note, right? So, so time is 56:50. We tried to jerry-rig this test to run in 4 passes for the 4 extreme corners in order to find edge cases of failure. But looking over the code, I find this test does not accommodate such a thing. We've written a lot of test code extra to figure out why this test was failing. We now know why. Let's just hard code the test for corner to target equal 1. The reason it does not fail on this corner is because that uses 0, 0 as the coordinate position, and no information is lost when switching to different tile size exponents. For example, the largest tile size exists on a 1 by 1 tile map, and its only possible coordinate is 0, 0. So if you switch from a coordinate where till x equals 0 to a coordinate where till x equals 7, largest, and back again to chord where till x equals 0, the conversion of the coordinate space will always be lossy unless you used chord 0, 0. So basically, I'm saying that the test code here, the test code I'm writing and trying to target these different corners is fundamentally flawed. The test code is fundamentally flawed in any case where we're not using coordinate 0, 0. And as such, we can salvage the tests by just only always targeting corner 0, 0, top left, right, 0, 0. We can salvage those tests because those were actually running beforehand. But when we tried to jerry-rig the test to, you know, cover a more thorough gamut of test cases, it started failing. We wondered what we were doing wrong, because we thought we were doing something wrong. And after analyzing this and looking at this for a few days, no, that's not the case. The case is that we just didn't know what the heck we were doing. So, what we can do here, before we get out of here, so this is like our function. We've lost. Unit test code gets out of hand. The ordering constraints as far as like what function belongs where, I don't care about as much. But what I do want to do is, before I run this function here, I want to create another function that's going to be called right before it to emphasize, and it's going to emphasize why this test can't do corner case, why this test can't target different corners, right? So we're going to say void and AAC 2020 P5D 1 OGL UTC why next test can't use corners. So I'm literally going to call it why next test can't use corners, which is, you know, a weird name, maybe a horrible name. But that's what we're going to call it. So we'll make a note of this. So since we're using such a weird name, we might as well make a note of when we did this. So this test code should give you insight as to why had to be reverted to only test for the top left corner and no other corner. Basically, there is information loss when converting between coordinate spaces, because different x values have different local coordinate ranges, right? So I really never want to ever look at this code once it's done, like this test code, right? You want to write it and kind of forget about it, as far as I'm concerned, because it just gets so ugly, right? You just want it to give it. The algorithms are not going to change. The algorithms for how this data structure works are never going to change. If I ever wanted to use different data structures, it would be a different subsystem that uses a different data structure, and it would be rewritten from the ground up. And because of that, I do have the luxury of saying, I'm going to write this test, and I'm just going to forget about it forever once it's done. So we're going to take this test name, and we're going to go find where this test is being called from. And right before we call this test here, so we call it, so we decided to, like, call it in this stupid, crazy loop thing here, right? And now, we need to just trash this, right? So we're gonna trash this looping structure around here, and we can keep this, sure, why not? And before we call this, you know, we can say, we're running out of room, right? So I'm going to write it really weird like this. And, extern void. How about define, no, even if we do that, right? God, this just sucks. Oh, well, let's just get fancy here. Define test name, and we're going to take this right here. I usually do not get this weird, and we're going to put it together with name, right? So, right, we're gonna use a glue macro to create this thing here, And then underneath here, did we delete this? Did we just delete this? I think we did. So let's look for UTC ... whatever. Yeah, I think we did. So hold on. So this print statement, we're going to keep the print statement. And actually, no, let's not keep it. Let's just get rid of that. So this test here, we know it's running, and we know that, yeah, the corner to target thing was just a bad idea. So we're going to say void. We're going to put void back in there. And then we're going to undef test right here. We're going to undef this test macro. And so we're going to create the test thing here. So we're going to get rid of the namespace here. And we're just going to say test, y next test, can't use corners, right? So we're just using that to create a name. And then we can just say extern void. And since we have the macro, we might as well do the same thing here, right? So we can take blah 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 UTC, right? Which is common here, right? And we can also do that here, right? So we can go test, wrap it like that. So usually I will not get this fancy with macros, but here we are. It's unit test code. I don't care as much. So, and this needs to be void, right? Void. Duplicate it, get rid of the extern thing here. Right? So, right, so we wrote it kind of weird. Just say so at vidID 109 time 0107 52. I never want to ever have to look at this test code ever again in my life. So, let's address what's going on here. After we kind of put this in a nice little block comment here, and say this got out of hand. This is hard to follow, right? Making this weird macro here to make this namespace. It makes things kind of rigid in a way that I actually don't like. But, yeah, because usually I'll only use macros for shortening names. I guess technically, once again, this is using a macro to shorten a name. So I guess I'm not breaking that habit, right? But usually I just use it as a quick name replacement, right? I don't do anything fancy like with this glue macro thing. But for this, it's just getting... The column space is getting out of hand. This is just getting ridiculous. So yeah, so why next test can't use corners? So we're going to go over there and say, well, why can't the next test use corners? And to answer that question, we're going to write this test code here. And we want to go PAINPix to CoveyPix. And once we go from paint pixels to covey pixels, we want to go back, right? And as we write this, we'll kind of see what the problem is. So I believe we should have like a CoveyPix to PAINPix. Let's put a little breakpoint here. So it's always going to migrate to the top left corner, is the problem. Yeah. So let's make a little table of test data, right? Let's make a table, I don't know, int32 table, unit test code, some amount of stuff in here. We don't know exactly what it is yet. And within here, we're going to say that the things we really care about are the tile exponent size. So we care about the tile exponent. TE, tile exponent. But we're not going to put the tile exponent in here, are we? You can actually do a test for different tile exponents. Yeah, we could do that. We could write it kind of weird, but we could say tile exponent, and then the TX, TY. Let me think about this. I don't know. I don't know how exactly I want to write this to emphasize what's going on. Let me put some breakpoints here. So there should be a coveypix to painpix, I believe. Let's see if that exists. Coveypix to painpix. And that would actually be over here. Nope. No such thing. It would lose information, though, that's for sure. I don't even want to write code for this. So, there is no such thing for this yet. Okay, there's no such function for this. If we look for this anywhere, we're not going to find it in any files. But we can look, we can make sure. Yeah, I don't want to make a function to emphasize why not to do this. When in reality, coveypix dot cov ix and coveypix dot cov iy. Yeah, screw this. We're just not going to write this. The fastest code is the code you don't write. So we're just going to leave it empty. Yeah, screw this. I'm just going to make a note here. Screw writing this. I would have to create a function, which I do not need, just to illustrate why a previous unit test was yeah, so let's not get stuck up in a gambler's fallacy kind of thing, or a sunk cost. Not gambler's fallacy. Let's not get caught up in the sunk cost of, oh my, I already stubbed in this function and whatnot, and it's already there. We're not going to get caught up in that. We're just going to say the time, the video is 109. Right? And screw this. Right? Yeah, we're done here. We're not gonna write this. Not if it didn't seem, if it were to be more trivial to where it wouldn't require me to write another little helper function that actually require this helper function would require quite a lot of effort to get this working. And all I wanted to demonstrate is that there's going to be some information loss, and we convert from PAINT5D to CoveyPix, right? CoveyPix to PAINT5D, and when we go back and forth like that, we're going to lose information, right? So PAINT5D, CoveyPix, right? Depending on the tile exponent, yeah, there's depending on the tile exponent. Now, if the tile exponent is 0, there will be no information loss when we do PAINT5D to CoveyPix, and then CoveyPix back to PAINT5D. There shouldn't be any information loss, but we'll start to lose. The coordinates will start to migrate to the upper left coordinate of the PAINT5D data segments, the local segments of data. So one of these like local segments here. The data will kind of migrate up into the upper left corner for these segments. As the tile exponent gets higher and higher and higher, because eventually, the only possible coordinate, especially when you're using tile exponent, 7, the largest tile size, the subdivision is just a 1-by-1 subdivision, and yeah, we lose data. I'm not explaining this very well. But the thing you want to understand is that these conversions are lossy. They're lossy conversions. They're not one-to-one conversions. They can be one-to-one conversions if the tile exponent were 0, then you can make these one-to-one conversions. But once the tile exponent is not 0, they're not one-to-one conversions back and forth. And that's the reason some of my unit test code was failing. I'm not explaining this in the best way. But right now, I am sick of this, right? I just want to get some code running, and I'm just sick of it. So let's just write a little commentary there. You know, we'll make sure that the brackets are balanced, just so that it doesn't do anything weird in my syntax highlighting. But besides that, no, I'm done with this. So the next thing we want to do, and also we can't even highlight this and find it because we did that weird macro nonsense, right? So we got to highlight the subsection to find where it's called from. And this test here, right, we removed the corner code from it. So so now that's getting harder to find because we got to look for the UTC in front of it, right? But yeah, this is UTC whatever the heck. Let's just hack this really quick. Let's take this, paste it onto here. But yeah, I'm kind of done with this to the point where it's like, I do not care right now. Yeah. But this function here, right, is this function here. So let's take a look at that for a second. So this function, it was working fine until we tried to target different corners. Different corners involved local coordinate addresses that were not 0, 0, and that's why things started failing. So we got rid of the coordinate enum, the corner enum in here. And then right here, we should be able to delete this nonsense here now. It should just work. The corner to target is always going to be 1, because we realized, nope, we were wrong about what we were doing. Just keep that 1. Keep that as 1. And for the corner to target, that means that when we use that corner to target, we're always going to get, where the heck are we even using it? Simple get put test corner to target. Yeah, so I think that if we do this, we'll actually get the code working, right? We'll actually get it compiling again without any unit test crashes. If I haven't messed up anything, well, that's sure a mess up. So Control G, 1934. And we were blah blah blahing, and at which time we made that mistake. Okay, cool. And we may have made some other stupid mistakes. But yeah, that test was already complicated enough. Expected declaration specifiers before return. Void. We can't do a naked return. Alright, well, if we can't do naked return, then just comment that out. Sure. I don't know if maybe it doesn't like the fact that the function is empty. Oh, still says declaration specifiers. Did we kind of like... Oh, we didn't balance this the same way. Got it. Okay, I can put that return back in. I just didn't have my bracket balancing correct. Yeah, so this is a disaster. And I want to just get the code running. Never have to look at this again. So, if this code fails, I'll be flipping a table. Okay, so we're in the I don't know why this test takes so long to run, but we're also going to have to think about turning off this test randomly as well, right? Because these tests take a long time to run as well. And I don't want to... Okay, cool. Yeah, so everything passes, right? Like, everything passes. Oh, wait. So my shortcuts sometimes interfere with the hotkeys, but yeah, these tests pass. So what are we going to do about the test code kind of like... Test code is starting to become a problem. And even though I don't want to make a global kill switch for tests, I think we're going to have to create a global kill switch for tests. I think that the global kill switch is going to have to go somewhere around the silence subsystem. So yeah, we're going to have to... Yeah, because otherwise, yeah, so, forget copying this. Yeah, we have enough stuff. So what we're going to do here is, to do, global kill switch for, unit test code. So with great power comes great responsibility, something Spider-Man. And what we got to be careful of is if we make this global kill switch, then we don't want if we make this global kill switch, right, there's the ability to just turn off all the unit testing, but that also, right, the danger of being able to turn off all of your unit testing should be kind of obvious. But I guess I should say it, right? That if we turn off our unit testing, we accidentally break something, a few months go by, and somehow it is not noticed. We turn our unit testing back on, things start failing. That's the situation I would like to avoid. But the thing is, if our tests start taking minutes to execute, then it's not very good for our development cycle, right? So it's like it's a dangerous situation that we're going to have to put ourselves into, because otherwise the development pace will be unacceptably slow. Even for me, it will be unacceptably slow. So we're gonna have to make some type of global kill switch for the unit tests. And then, it doesn't mean we have to put it everywhere, right? Like, just because we have this global kill switch class, doesn't mean that it has to be implemented anywhere, right? Because everywhere we're going to implement it, the only reason we're going to implement the global kill switch is to save time when we're starting out the project, right? So if we have places where it's like, oh, this doesn't take long to test this stuff, then maybe we won't put the kill switch there, right? We want to make it kind of hard to remove code, remove test code. Okay, so with that, let's look at our git bash here. Git bash, git status, can't spell, git add dot, unit testing for life. Unit testing for life vid IID. We'll push up to GitHub, and then we're going to rerun this project one more time, make absolutely sure that it actually is running without crashing. But yeah, we have plenty of unit tests. Like, we have a ridiculous amount of unit tests. Most of our code is unit tests, right? Like, most of the code is unit tests. Yeah, and the idea is to have a very strong foundation, right? We don't want to build on top of a shaky foundation. That's why most of our code is unit tests. So yeah, let's just run this one more time. Make absolutely sure that indeed, like, all of our tests are passing, and that the executable starts up. And from there, we're going to push this up to Kanji Coder. And then before we end the stream, because I don't want to... Before we end the stream, we want to put in a kill switch for unit tests. So, I guess UTC killer. So unit test killer, so UTC kill, you could call it, because unit test kill, that is 7 letters, right? So let's suspend hotkeys. Okay, cool. So there are other things that I wanted to stub in terms of code, in terms of, like, pieces of the project. So I need to go upstairs really quick and be like, what? There were 2 other kind of things that I wanted to stub in. One was a keyboard listener. And another thing was I forgot what it was, but there's like 2 other things. I have them as notes on a piece of paper in the shower. I got waterproof paper for the shower. And I want to take a look at that and say, you know, I'm about to stub in these other subsystems, so we should probably stub them all in right now, because it's going to be a tedious process to stub those in. So what we're going to do here is we're going to do git status, git push Kanji Coder. I'm going to push this to Kanji Coder because now it's compiling, and, right, so if you want to test it out, you can test it out, right? Okay, cool. So yeah, I'm going to go upstairs really quick and look for that. I guess technically I could just stop the stream now, because I could stop the stream now because we just crossed over into another day. So it might make sense to stop the stream, because right now, since it's another day, we might want to change the day, right? Say it's Wednesday now. We didn't get much code done for Tuesday, but we were all over the place for, but we were all over the place in terms of doing work on Monday, so it's understandable. We got our push-ups done for today, though, so we got a little work done. We got like 2 hours of work done, I think, today, on Tuesday. Monday, we got 16 hours, so I feel like the coffee doesn't really make me more productive. It just shifts where my productivity is. But that's fine. So total today, we're going to drop total today back down to 0. Because it's no longer Tuesday, it's Wednesday. And then we're going to stop the stream, and we'll be back once I figure out what systems I want to stub into place, and I'll change the video number to 110.